Okay. So hello everyone, this is week 6 of the ACE CAD group. For those of you who are in the WebEx, I already said this, but I'm just gonna run it through for the recording. Firstly, we're gonna go through stress analysis and Inventor. It's not gonna be a long this topic, but it's pretty cool and intuitive what Inventor can do when it comes to stress analysis. And then after that, anyone in the WebEx can ask questions about the project. You have until Sunday, which is the 14th, to decide if you want to do the project or not and make your decision. And then after that, something I found rather recently that I found pretty cool. It doesn't have to do with CAD or 3D modeling or 3D printing exactly, but it's the Microsoft Hololens, which is a pretty cool piece of what they're calling mixed reality technology. So I'll play a video about that at the end just for information's sake. So like I said, we're going to go into stress analysis and Inventor. So the usefulness that this application has to manufacturing can't be overstated. They can make their model, they can select the right materials they want, put it under whatever stress and just see how it would react without actually putting it together and wasting material, time, and money. I put dozens here. When we go into Inventor, you'll see it's probably close to 100, maybe more materials, different materials ranging from aluminum, steel, plastic. So they have all different types of materials. And you can also take your stress analysis and turn it into animations. So you can use the animations for further analysis or just a presentation. If you want to put the video of a presentation for a new part you're making, you can do that too. So you can use this on any part, which would be found in the 3D modeling ribbon. And it'll be all the way to the right, stress analysis. I don't have a picture of it, but you can also use it for an assembly. And in the assembly, you'll have an environments tab, and that's where you can find the stress analysis for an assembly. Once you click on stress analysis, it'll make a whole new ribbon up here, and you just need to click create study, and then you just need to name what kind of analysis you're doing. If you want to do different pressures, different forces, different orientations, you can name it all different things. You can have 10 different studies all going on at once. And you just need to click OK after naming it.
Okay, quick question.
Yes.
Are you sharing anything?
Oh my goodness. No, I am not. That's what I forgot to do. Alrighty then. Okay. Well, besides this slide, nothing other images are really that important. So thank you for that, Kevin. Okay, so going back one slide, you can use this in any part or assembly. For when you're using a part, you can just go to the 3D modeling tab in that ribbon and be all the way to the right. If you're using an assembly, it'll be under the environments tab, and it would just be the same thing, stress analysis. Once you click stress analysis, it'll give you a new ribbon. You just need to click create study and you can name it. And like I said, you can have 10 different studies going on at once for different forces, different orientations, whatever. Okay. So now the basics of using the stress analysis. It literally is a step-by-step process of setting it up, and it will stop you if you try to move on just to make sure you have everything. So on the left side, you'll see material, constraints, loads, contacts, mesh, and then your results, or solve, simulate. And at the top in the main ribbon, after you click create a study, all these tools are usually grayed out, but once you start your study, all of them will become available to you. And it just goes in the same order. You have your material selection, you have your constraints, all your different loads, contacts, mesh view and mesh settings, and then simulate. So the material, these are just quick descriptions, but again, once you're in Inventor, you can just mouse over them and you'll get an even better explanation and an image to help you make sense of it all. But like I said before, you can make it out of aluminum, steel, PET plastic, rubber, whatever. They have tons of materials. Your constraints is how your part or where your part will be fastened. So, for example, if you want one side of it to be welded, you would fix that end. If you want both sides to be fastened in some way, you would just uh, fasten that end. Then your loads are different types of stress. So you just have a straight force, which applies a force to a face in one location. You have pressure, and then also moment forces, which is like rotational forces, gravity, cylindrical. So you have all different types of loads. Contacts is when you have multiple parts, and it just sets how these parts will be in contact with each other. If you have a single part, you just click, I'll show you later, you just click automatic, I believe, and it will just automatically generate them, and it's just a single part, so there should be none. And then mesh is just how the program views the part, and if you have smaller mesh intervals, it just means the simulation will be more precise. Typically, the default setting is good enough, but just in case. So in terms of interpreting the results after you run your simulation, depending on your part, this is something I made. It's just a square pole. I think I used aluminum. So you see up here that says type, the von Mises stress. Um, for this type of stress analysis, you just need to know the yield point or yield strength of your material. And as long as your maximum does not exceed that yield strength or yield point value, it could be considered a success. Your material or part wouldn't fail. Just the unit note, KSI is kilopounds per square inch. So you just gotta multiply this by 1,000, you get pounds per square inch. And now again, I'll show you when we're in the program. After you simulate, in that ribbon at the top, you will now have the result tab available. So then you can make animations. You can set certain probes up to test the stress in a particular area or convergence, which we'll get to later. And then I encourage you just to play around with them yourself and just see how it works in general. So now we're going to do a quick example with that square pole thing you saw me make. So actually, I'm just going to go back to the home page and start over. I was messing around a little bit. Okay, so give me 1 second. I'm going to stop sharing real quick. Does anybody have any questions before I continue into the Inventor? No? Okay. Okay, so I'm going to go back to sharing. Sorry, I had to. Oh, sorry, I wasn't looking at the chat. Um, there are, and I'll show you when we get there. There are different ways of analyzing the results. One of them is even just simply displacement, how far the part would move. But I'll show that when we get there. I'm having, okay, share content. Okay. So here we are, we just have our standard square pole piece. I made it 2 feet long, just for your reference in terms of scale. So again, in the 3D modeling section, we just have a part here. We're just gonna go all the way to the right, and we have our stress analysis. And again, so all of this is grayed out, and we only have the option to create a study. So I'm gonna create a study, it's gonna bring this up. I'm gonna name this, we're gonna say weld, I can spell, weld both ends. Again, can't spell. So now, again, it's just the checklist. So first we want to assign our material. And again, these are all the different materials. So we've got probably dozens or so. I'm going to use the aluminum 6061, and we're going to use the yield strength. You can also use ultimate tensile strength, both of which are very easy to find. You just need to search up your material and then yield strength, and it'll probably tell you both. For aluminum 6061, I believe the yield strength was 35,000 PSI. So as long as the force exerted on your piece does not exceed that, your part won't fail or break. So we have our material. Now our constraints. You have fixed constraints, so it constrains motion in all directions. You have a pin, so it can move radially, or frictionless, which prevents motion of a face in the direction normal to the face. So if I put it couldn't move this way. If I put a frictionless constraint over here on this face, on the side. But we're just going to use a fixed constraint, and if you were to weld this, you would be welding the outside. So I'm going to select all the outside sides, and I'm just going to go the other side as well. And there we go. We just have all of our selected sides, and we're just going to press apply. Now that's all done. Next on the list is our loads. So I'm just going to put a force right in the middle of this face. Now you notice that it is in newtons. If you want to just use pounds, when you type in your force, let's say we want to put 200 pound force, you see to put 200 and then LBF, which is pound force. You can't just put LB or LBS. You have to put LBF. And we want it pushing down on it, so that direction is fine, and we just click apply. And it automatically converts it back into newtons for magnitude. And you can also use vector components if you wanted it to be in a certain location or pointing in a certain direction. Again, our contacts from before, we have a single piece, so we can just press automatic and it just generates that. We're just going to turn on mesh view so it's easier to look at. And that's it, we're ready to simulate. So when we press simulate, we're going to run it. And there we go, we have our analysis. So again, up here we have our von Mises stress. I'm sorry if I'm saying that wrong. But we notice that the maximum value, which is actually right down here at this point down here, our maximum value would be, if we convert that to PSI, would be around 550 if we round up PSI. So not a whole lot from a 200-pound force, which is, we can think of it just as being like an aluminum ladder. You're walking up an aluminum ladder. It's not gonna, hopefully it's not gonna break. I mean, but so yeah, aluminum, I believe again has a yield strength of 35,000. So this is not gonna be an issue at all. And to your question, we can do different stresses. We have first principle stress, which I actually don't know how these different stresses work. I only know about this one. But you also have displacement. So this is only going to move, half of a, I guess, milli-inch, because we're using inches. So it's not going to really move a whole lot. Again, if you're walking up a ladder, it's not really going to move. And then you also have a safety factor, which we're all good. And then let's just say you only wanted to weld one end. So again, I can finish analysis. And I wanted to make a stress analysis. And for whatever reason, you wanted to only weld one end and try like putting a force on the end over here. So we can try weld one end. We can just start a whole new study. We're going to assign the material to be the aluminum 6061 again. We only want to fix the one end. We want to put a force, and instead of just clicking the face, I'm going to go over here and click the edge. And now you notice how it's going parallel to that edge. What we can do is, for the direction, we can click right here. We want to select our direction, and we want to go in the direction going downward. So we can select this side right over here. So now it's pointing up, but we can just flip it around. So that's how you can use the direction tools over here. It just puts it in the same direction as the edge that you select. And again, so you want to put 200 pounds of force. Just apply that. And now I think it just, yeah, just hit itself, but it's right there. It's on the end. Put 200 pounds of force on the end. And that's it. That's all done. Automatic contacts, mesh view, just to see the different parts and simulate. And now you see that we have a much bigger maximum force exerted on the end over here. It's about, it's 6.84 thousand pounds per square inch. But according to our yield strength, that is still enough to not break. It would still hold on. And then you can check the displacement. It would move, 0.05, again, if we round up, of an inch on the end. So again, this is just all different tools you can use for testing this. But that's it. Beyond that, it's just a matter of hopping in and messing around. You also have pressure, which applies a uniform pressure to the entire face. So like when I selected force, it put it right in the middle. But if you wanted to apply a 200-pound force over the entire top, you would use pressure. A moment force, again, you can hover over and it tells you. So if you select a planar face, the face normal vector establishes the moment. So the moment would be the axis of rotation. So if I selected the side, it would exert a force that goes like in this direction or this direction, a rotational force. Um, but that's about it. And if you want to animate it, so we want to make it 20 steps, normal speed, we can just make a animation of our part going under this stress. And that's it. Probes. You can measure simulation results, as you can see in the picture, at certain points. And you can also make a convergence plot for higher end analysis. But that's it. I'm going to stop sharing my screen. Are there any questions in the chat about stress analysis? I'll give it a second in case someone's typing. Okay, so now does anyone, Dom, Vishal, or Ethan, do you guys have any questions about the drone project? Do you know for certain if you want to do it? We can put you down now. If not, again, you have until Sunday. Um, any questions at all? None right now. Do you think you're gonna want to do it, Ethan? If not, it's okay. We're purely just asking. Okay, that's fair. I was talking to Vishal earlier, and yeah, the time, especially with classes being online and other activities. Um, Hello? Yeah, what's up, Dom?
Oh, how do we? I mean, I think I'm gonna want to do it. How do we do we just put in Discord or something?
Um, yeah, so you can just, I mean, if you think you're gonna do it, I can just put you in our record, make a note of it right now.
Yeah, sure.
Do you think you're gonna want to do it with a partner, alone?
I think I'll just do it alone.
Okay. And then, do you know which type of drone you want to design?
futuristic.
Okay. Okay. I got you down. You're good. And that's it, I believe, for now. So I think I'm just gonna show the quick video on Microsoft's introduction to the HoloLens, just to show a little bit about that. Okay. Can you guys hear it, or did I mess up the sharing option?
Don't hear anything.
You don't hear? Okay, I have to stop sharing and okay. All right. How about now?
Yep, I can hear it now.
Okay, cool. Sorry, I was muted. They also have it on their website. Um, you can just scroll through and look. I thought this was pretty cool because this definitely could have 3D modeling. Can you guys hear me?
Yeah, we can hear you.
All right, WebEx just told you couldn't hear me, but all right. This definitely has potential 3D modeling applications. But yeah, that's it. I just thought this was rather interesting to share. But I think that's it for now. Um, just for the recording's sake, if people end up watching this Sunday the 14th, we would like if you guys could declare if you want to do the project or not, just so we could maximize the amount of time we can give you for it. And I think that's it. Uh, if you guys have any questions, if not, I think this meeting's over.
I have one question about the drone project. So,
Yeah.
if Dom's doing it alone, should I do it alone too? Like, is there anyone else? Or like, I don't know if I want to do it alone or not alone yet. So, like, is there an option to work with someone? Like, is there anyone else working on it?
As of right now, we haven't gotten any other responses. But I could put you down as like a maybe and looking for a partner, and we can like put that out there that like if someone else is in the same situation as you, they're thinking about doing it but don't want to do it alone.
All right, got you.
Yeah.
All right, sounds good. Thanks.
Yep. Okay, I think that's it, guys.
Nice. Thanks,
Yep.
Al. See ya. See you,
See ya.
everyone.
Alrighty.
Jeez, I forgot what I was gonna say.